Question 1. Sulfur trioxide is produced through the following reversible reaction which occurs at a temperature of 400 degrees Celsius. So this is the reaction that is taking place, and we have delta H is less than 0. And since delta H is less than 0, so delta H is going to be on the product side. Now, the first question was, which of the following is a disadvantage for using a high temperature? Now, if I use high temperature, then the reaction is going to shift to the left side, decreasing the yield of the reaction. So I will have less SO3 produced. So the disadvantage of using high temperature is that the yield of the reaction is going to decrease. Now, which of the following is an advantage for using high temperature? Now, when we use high temperature, the rate of the reaction is going to increase because we're going to have faster molecules colliding with each other. So select the molecular geometry of SO2 and SO3. Now, to solve this question, first I will use the have and need method. And I'm going to start with SO2. Now for SO2, I have to first count how many electrons do I have, how many valence electrons do I have. So sulfur has 6, oxygen also has 6, but I have 2 oxygen atoms, so I have 12 plus 6, so I have 18 electrons. So first I'm going to draw the S, and I'm going to connect the sulfur with the oxygen atoms. And since I drew 2 lines, so I used 4 electrons, so now I'm left with 14 electrons. Now for the need part, I have to check how many electrons does each atom need to satisfy the octet. This oxygen needs 6, this sulfur needs 4, and this oxygen needs 6, so I need 16 electrons to achieve the octet. However, I only have 14. And in the case where the have is less than the need, then you have to draw another covalent bond between the atoms. So you can draw a covalent bond between the sulfur and this oxygen atom, or on the sulfur and the oxygen atom on this side, on the left side. And then you can count again how many electrons do you need for each atom to satisfy the octet. So this oxygen needs 6, this sulfur needs 2, and this oxygen needs 4. So now I'm left with, I now have 12 electrons after drawing this line, and I need 12 also electrons to satisfy the octet. So I can now use the electrons that I have, the 12 electrons, to and distribute them as lone pairs on the oxygen atom and on the sulfur. So here I'm going to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I have the shape for SO2. So SO2 has the AX2E, where A is the central atom. I have 2 atoms connected to sulfur, and E stands for the lone pair. I only have 1 lone pair on the sulfur. And AX2E stands for a bent shape. So SO2 has a bent shape. Now let's go over SO3. Let's do this method again. So for SO3, I'm going to also use this table, have and need, and I'm also going to write SO3. Now S has 6 valence electron and oxygen has 6, so I have now 6 times 3, 18, plus 6, so I have 24 electrons. I will first draw S and connect the oxygen atoms with the sulfur atom. And then I'm going to count how much electrons have I used and how much do I need to satisfy octet. So I've used 1, 2, 3, 4, 5, 6 electrons, so I now have 18. How much do I need to satisfy octet? Oxygen over here needs a 6, this oxygen needs a 6, and this needs a 6, and the sulfur needs 2. So I need 20 electrons to satisfy octet, and I do not have enough electrons. So I have to draw another covalent bond between sulfur and an oxygen, and I can pick any oxygen atom. I'm going to use this oxygen atom, and then I'm going to cancel and write over here that I have now 16, and I'm going to count again how much electrons do I need to satisfy octet. This oxygen needs 6, this oxygen needs 6, this oxygen needs 4, and sulfur doesn't need any electrons, so 12 plus 4, 16. So now, because I have the have is equal to the need, now I can distribute the electrons on the oxygen atom. So over here I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here I will have 13, 14, 15, 16. And the shape of SO3 is AX3. So SO3 is going to have a trigonal planar shape. So this one, SO3, is going to have the AX3, whereas SO2 is going to have the bent shape. So then we have, in this question, 1 mole of sample of sulfur dioxide and 1 mole sample of oxygen gas were introduced into a sealed flask and allowed to reach equilibrium. At equilibrium, the total pressure in the flask was 1 times 10 to the power of 5, and the equilibrium mixture contained 0.8 moles of sulfur trioxide. And they said determine the mole fraction of each component in the equilibrium mixture, including SO2, O2, and SO3. So first I have to rewrite the reaction and of course use an ice table to find the number of moles at equilibrium, and in order to find the mole fraction, which is Ni over the N total. So I did the ice table over here. I have 1 mole for SO2 as per the given, and 1 mole for O2, and 0 moles for SO3. Then I have minus 2x for SO2, minus x for O2, and plus 2x depending on the coefficient. And of course I have plus over here because the reaction is going to shift this way since I have a 0 over here. And this is the values at equilibrium. Now they said that the equilibrium mixture contains 0.8 moles of sulfur trioxide. So at equilibrium, the 2x should be equal to 0.8. So x is going to be equal to 0.4. Substituting these by x, I will get the number of moles for the SO2, O2, and SO3, and I can find the number of moles, the total number of moles. Then I can use the formula, which is the mole fraction, to find the values. So the mole fraction for SO3 is going to be equal to the number of moles of SO3 over the N total, and I will have 0.500. I add the zeros because they need 3 significant figures. The mole fraction for O2 is going to be equal to 0.375 by dividing the number of moles of O2 by the total number of moles, and the mole fraction for SO2 is going to be equal to 0.125. Now, in this question, they asked me to calculate the value of Kp for the reaction and to state its unit. Now, Kp has the same formula for as Kc. It's the products over the reactants. However, you're going to use pressure instead of concentration. So you put the pressure of SO3 squared divided by the pressure of SO2 squared times the pressure of O2, and you raise them to their coefficient. And then you need to find the values for each pressure, and to find the values for the pressure, you need to do the mole fraction multiplied by the total pressure. Now the total pressure is given as 1 times 10 to the power of 5, and the mole fraction, we already got it before, so I multiply the mole fraction by the total pressure and I will get the value for each one of them, and then I plug them in this equation and I will get 4.26 times 10 to the power of minus 4. They need 2 significant figures, so I will put 4.3 times 10 to the power of minus 4. And to determine the unit, here I have Pascal squared over Pascal squared times Pascal. So these are going to cancel. I'm going to end up with 1 over Pascal, and so I have Pascal to the power of minus 1. Now in question 2, choose the correct answers to predict the effect of the given changes on the equilibrium position for each of the following reactions. This reversible reaction, and it's an exothermic, so I directly like to put the delta H as a product since it's an exothermic reaction to determine how equilibrium is going to shift. And then I can start solving for each change. Now for the first one, I have increase in temperature. So if I have an increase in temperature, then delta H is going to increase, and the system wants to decrease delta H, so the system is going to shift to the left. So for the first one, it's going to be left. For the second one, I have an increase in SO2. An increase in SO2, system is going to shift to the right to counteract this change. So the equilibrium position is going to go to the right. Increasing the pressure. If I increase the pressure, the system wants to go to the side where I have less moles of gas. In this side, I have 3 moles of gas, and on this side I have 2 moles, so it's going to go towards the less number of moles, so it's going to go towards the 2 moles of gas, so also right. And when you add a catalyst, the equilibrium position is not affected, it's just attained faster. So over here, I'm going to put no change. In this other reaction, this is also a reversible reaction, and it's now an endothermic reaction. So delta H is going to be on this side, and I'm going to include it as a reactant. So the first one was increasing the temperature. So when you increase the delta H on this side, it's going to shift to the right. The system is going to shift to the right to counteract this change. So the first one is going to be right. Increasing H2, so system is going to shift to the left to decrease H2. And increasing pressure, you will go to the side where you have less moles of gas. On this side, I have 2 moles of gas. And here I have also 2 moles of gas. So because the number of moles are equal on both sides, so there's going to be no change. And the same thing for the catalyst, no change. The catalyst doesn't affect the equilibrium position. Question 3. Before the equilibrium state of a reversible chemical reaction is reached, the rate of the forward reaction decreases because when I'm reaching equilibrium, the forward reaction is going to decrease forward, whereas the reverse reaction is going to increase. So the first thing we need to put over here is that the forward reaction is going to increase and the rate of the reverse reaction is going to decrease. Now at equilibrium, the rate of the forward and the rate of the reverse reaction are going to be equal to each other, and the concentration of reactants and products are at equilibrium are going to be constant. They will not change. Now, chemical equilibrium is referred to as dynamic due to the existence of 2 opposing processes. We have the forward rate and the reverse rate, and these processes are dynamic and we cannot actually see them, so we call them microscopic processes that continue to take place simultaneously at the same rate. They happen at the same rate with no macroscopic changes. So you cannot see any change with your eye. So no macroscopic changes. Now, we need to select the correct graph that indicate the changes of the rate of the forward and reverse reaction before and after equilibrium is reached. So at equilibrium, the forward rate is going to decrease, the reverse rate is going to increase, and after equilibrium, they're going to have the same rate, exactly the same rate. So the correct one is this one. This is not correct. The reverse rate actually increases and not decreases. And here we do not have the same rate. So this is the correct graph. Now for question 4, they said choose the correct answer to fill in the blank, predicting the effect of the given changes on the equilibrium and the amount of SO2, Cl2 produced. So when Cl2 is removed, this is Cl2, and when it is removed, so I have a decrease in Cl2, the system will try to increase Cl2 by shifting towards it. So it's going to shift towards the left. So it's going to shift backward. And the amount of SO2, Cl2 is going to decrease since it's going in this way. So Cl2, the SO2, Cl2 is going to decrease and the equilibrium is going to shift backward. The reaction is going to shift backward. And when SO2 is added, the equilibrium position is going to shift to the right. So we're going to say forward, shifts forward. And the concentration of SO2, Cl2 is going to increase because it's shifting this way. Now here I have to choose the correct answer to predict the effect of changing temperature on the following chemical reaction using Le Chatelier's principle. So as temperature decreases, when I have this reaction over here, I need to look at where temperature is. So you need to think of it as it's the 192 kilojoules. It's the energy that I have on this side. So as temperature decreases, the equilibrium position. So if this decreases, the system wants to increase it again. So it's going to go towards it. Whenever you decrease something, the system wants to increase it. So the equilibrium position is going to shift backward. because to restore this, let's say this energy, and the concentration of SO3 is going to increase because it's shifting toward this side, so SO3 is going to increase. Now for the other one, as temperature increases, the equilibrium position. Now this is delta H is negative, so I like to put the delta H as a product since it's an exothermic reaction. So if I have an increase in delta H, the system wants to counteract it and go towards the left side, wants to decrease the delta H. So the equilibrium position is also going to shift backward. And the concentration of CO2, which is over here, because the system is going this way, so the CO2 is going to decrease. Now, question 6, they said choose the correct answers to predict the effect of adding a catalyst on the following chemical reaction using Le Chatelier's principle. So, if I add a catalyst to this reaction, the equilibrium position is going to be attained faster using the catalyst, and the concentration of CO2 is going to remain constant because a catalyst only allows equilibrium to be reached faster, but it does not change the concentration of the product or the reactant. It just speeds up the reaction. Now question 7, dinitrogen tetroxide and 2O4 and nitrogen dioxide NO2 exist in dynamic equilibrium with each other. This is the diagram that I have. It's the reaction pathway and the energy. And I have delta H is plus 45, which indicate that it's an endothermic reaction. Now, the first question was, choose the correct number that represents each of the following, the activation energy of the forward reaction. So this is the reaction pathway, and the activation energy is the energy needed to transform the reactants into the high peak, which is called the activated complex. So the activation energy is 2, which is from this part to this part. So the activation energy is going to be the number 2. Enthalpy change of the reaction. The enthalpy change stands for the change of energy between the products and the reactants, which are NO2 and N2O4. So it's going to be 3. And the value of changes if a catalyst is added. Now, if I use a catalyst, the graph is going to be something like this. The activation energy is going to decrease in the forward direction and in the reverse direction. So what's going to happen is that the activation energy of the forward reaction, which is 2, is going to be less. And the activation energy where I'm going from NO2 to the N2O4 is also going to be less, and this is 1. Now, the enthalpy change is not going to change. It's going to remain the same. So the only thing that will change is 1 and 2. So the value of 1 and 2 are the ones that are going to change. Now, in the next question, they said, drag and drop to check how the yield of the reaction is affected when each following change is applied to the system at equilibrium. And by the yield, they mean the amount of products. So let's write the reaction again over here. So this is the reaction. It's N2O4 plus delta H, and it's giving 2NO2. And the first question was, what's going to happen if I increase the temperature on the yield? Now, if I increase the temperature, since it's an endothermic, an increase in delta H will shift the reaction to the right because the system wants to decrease delta H. Since it's shifting to the right, there will be an increase in NO2, which is the product, so the yield will increase. So the first one, the yield of reaction increase. Now, the second question was reduce the volume. Now, if I reduce the volume, the pressure is going to increase, and the system wants to decrease the pressure by shifting towards where I have less moles of gas. Now here I have 2 moles of gas, and here I have 1. So it's going to shift towards this side, since I have 1 mole and here I have 2 moles. So it's going to shift to the less number of moles of gas. So it's going to shift to the N2O4. I will have less NO2. So in this case, the yield of the reaction is going to decrease. Now adding H2 gas, when I add H2 gas, it's not part of this reaction, so the yield of reaction is going to stay the same. Nothing's going to change. Now for this question, a sample of 0.06 mole of N2O4 is introduced into a flask and allowed to reach equilibrium. N moles of N2O4 react to reach equilibrium where pressure is 1 times 10 to the power of 5 Pascal, and this stands for the total pressure. Now they said write the mole fraction in terms of N. Now whenever they say equilibrium and the mole fraction, I have to first do an ice table where I'm going to use the moles. So this is the ice table, this is the reaction. Initially I had 0.06 moles, and here I have 0 because no NO2 was introduced. Then I put minus N, since they said over here that N moles of N2O4 reacted. And here I'm going to put plus 2N using the coefficient over here. And then I'm going to add these two terms, 0.06 minus N, and here I have 2N. Now N total, I'm going to add these two values, and I'm going to end up with 0.06 plus N. Now to find the mole fraction for NO2, I need to use the formula N over N total. So how much moles do I have of NO2? I have 2N, so I have 2N over here, and the total number of moles are 0.06 plus N. So it's going to be 2N over 0.06 plus N, the mole fraction of NO2. Now, for this question, they said calculate the value of Kp and write its unit if both gases have the same mole fraction at equilibrium. So the formula for Kp is the pressure of NO2 squared over the pressure of N2O4, because the reaction, it's reversible and we have 2 for NO2, so I have to raise it to the power of 2. Now, this is the expression, and they said that both gases have the same mole fraction at equilibrium. Now, the mole fraction is X is P over P total. So P of NO2 is equal, if I do a cross multiplication, P of NO2 is equal to the mole fraction of NO2 times the P total, and the pressure of N2O4 is equal to the mole fraction of N2O4 multiplied by P total. Now, since these two values are equal and the P total, they're also equal to each other, so the pressure of NO2 is equal exactly to the pressure of N2O4. So instead of writing this, I can write P squared of NO2 over the pressure of NO2. And I can cancel them, and I will get the pressure of NO2. Now, since the total pressure is 1 times 10 to the power of 5 Pascal, so therefore, since we have the same pressure for both gases, so if I divide it by 2, it's going to be equal to 50,000 Pascal. So it's 5 times 10 to the power of 4. And since they need two significant figures, so I'm going to put 5.0 times 10 to the power of 4. And they asked about the unit. So we have Kp is equal to P of NO2, and the pressure is in Pascal. So the unit is going to be Pascal also. Now, question 8. In this question, we have to drag and drop the correct item to complete the table below with increase, decrease, or no change for each imposed change, given that one change is imposed at a time. So each change is done at a time, and do not fill the gray box. Okay, so the first one we have is add NOCl. So this is the reaction. We're adding NOCl. So NOCl increases, system is going to shift to the right, and to counteract this change. So what's going to happen is that NO is going to increase and Cl2 is also going to increase. Let's go over the second one, decrease the volume. Now, if we decrease the volume, pressure is going to increase. System wants to decrease pressure by going towards the less moles of gas. And here I have 2 moles of gas, and here I have 3 moles of gas. So the system is going to shift towards the 2 moles of gas and is going to go towards the left. So NOCl is going to increase, NO is going to decrease, and Cl2 is also going to decrease. Now, increase the temperature. I have to know if this is an endothermic or an exothermic reaction, and it's mentioned over here that this is an endothermic. So let me put delta H on this side. And now I can think of the outcome. So if I have an increase in temperature, increase in delta A, system is going to shift towards this side to counteract this change. So NOCl is going to decrease, NO increase, and Cl2 will increase. Add N2. N2 is not part of this reaction, so there will be no change, no change, no change. Adding a catalyst only makes equilibrium to be reached faster, but it doesn't affect the concentration, so it's also no change, no change, and no change for Cl2 when you add a catalyst. Now for question 9, use Le Chatelier to predict the shift of equilibrium position if the pressure is increased by decreasing the volume. So since pressure is increased, the system wants to decrease pressure by going towards the less number of moles of gas. Now the first one, we have carbon plus oxygen gives CO2. First, you need to be aware that this is a solid, so we cannot count it as a mole of gas. Here I have 1 mole of gas, and here I have also 1 mole of gas. So since we have the same number of moles of gas, then there's going to be no change. Now in the other one, I have to think, where do I have less moles of gas? I have here 2 moles of gas, here I have 3 moles of gas. So it's going to go toward the 2 moles, so it's going to go backward. Now for this one, I have 2 moles over here, 3 moles over here, so it's going to go in the forward direction. And here I have 2 moles of gas, and here I have 2 moles of gas, so there will be no change. Now the last question, select the picture that represents a state of equilibrium. Here I have a constant blue flame of a Bunsen burner. Now a Bunsen burner is a steady state. It's an open system. And equilibrium only occurs in a closed system. So because here over here there's an introduction of a gas and there are things that are changing, it's not a closed system, so it's not equilibrium. If I go to this one, the river is also a steady state because the water can be coming from the rain, snow, or so we will have something that's entering the river. So this is also a steady state, it's not equilibrium. Now, an unopened bottle of sparkling water is a state of equilibrium because it's a closed system. So the correct answer is this one.